Good morning, everybody. Oops.
Morning.
Good morning, good morning. Let's see here. Let's see now. Here. There we go. Let's see here. So, just turn on my camera here. Right. So, when we left off last time, we were talking about the propagation of random uncertainty. And let us see here. So, in that case, let's see. Let's see, that was 1231. That was so this says 34. Okay, so this is a solved one. So let's go ahead and go on and do this one as unsolved. This is what we're trying to do is find out the random uncertainty in a 0.25 molar. What? Oh, I see. That's the answer there. So 36. It says 34. Make sure I got the right one here. 34. I think it's probably this one. 0.25 molar, which are 6.4. Oh, this is micro. I see. I've done both of these. Okay, so let's do. So I think it's probably this one. So sorry for the confusion there. I'm back. There's a what we're working on is computing the random uncertainty, right, of a solution given a bunch of random uncertainties in the ingredients for this calculation, right? So this is a done deal, right? We prepared a 0.25 molar ammonia solution, right? We know it's 0.25 so long as the ingredients that we used are all correct, right? But we know that the ingredients have some uncertainty, right? We used 8.46 plus minus 0.04 milliliters of 28 plus minus 0.5% ammonia and diluted it to 500 plus minus 0.2 milliliters. Okay? And the density here of this is actually kind of screwy. This is the density of the 28% ammonia there. So, and the exercise is to find the uncertainty in the 0.250 molar answer. So let us see if we can do that here. The way that I would start this is again, we need to find the formula. And I like to find a single expression or formula that it encapsulates the entire process, or that is the entire process. The entire process, right? So that way we have all of the ingredients from start to finish all in one expression. We can see how they go together. Right? So in this case, we want to find the answer. Formula for the answer. Okay. That is 8.46 plus or minus 0.04 milliliters of NH3 concentrated solution. Okay. Kind of a long name, right? I'm going to multiply that by 0.899 grams. It also has a plus or minus 0.003 grams per milliliter. Then this guy, so this goes from milliliters of solution to grams of solution. Milliliters of ammonia concentrated solution, milliliters of that solution, grams of that solution. And once we're at grams, we use the percent weight to extract the amount or the grams of ammonia. 28.0 grams of NH3 for every 100 grams solution. And this has a plus or minus 0.5 on it. multiply by the molecular weight here. So there's 1 mole of ammonia. That'll be 17.031 grams. So just to review for me, we start with the volume of ammonia solution. We use the density to get the weight of ammonia solution. We use the percent ammonia to get the grams of ammonia. Then we use the molecular weight to get the moles of ammonia. And then we're going to multiply this by 1 over 500.0 plus minus 0.2 milliliters. And then multiply that by 1,000 milliliters per liter. And this is all equals 0.2508 moles of NH3 per liter of solution. Now the only question that we have left is, what is the uncertainty in this answer? Right? So we have to fall back onto our rules at this point. What is the rule for the propagation of uncertainty? And that rule is that the percent errors in each of these multiplication and division add in a root sum squared. So we can find each ingredient with an uncertainty here. 8.46, 0.899, 28. This one is exact. And then 500. And we're going to take each of these as a relative uncertainty. Not necessarily percent, but a relative uncertainty, right? You can also do it as percent. But let's just do it as relative uncertainty. And we can say we're going to take the square root of first this guy over this guy. Right? We're going to square it and put it in the square root. And we're going to add it, the remaining uncertainties. This guy over this guy. This guy over this guy. Okay. And then that's exact. And then this over this. And we'll take the square root of all of these. And this will be the relative uncertainty in the answer. There we go. So, now this, as it happens, is equal to so there's 4 zeros. Plus Oops. Okay, so 4 zeros, 2 zeros, and 6 zeros. All right. And then we can multiply this by 100% at the end. All right. And then this will equal 0.0000353 square root of that. Okay. So what I wanted to show you a little bit was where this number came from. So if we look at the second to last term, 0.5 out of 28, we'll notice that it is quite a bit larger than the other terms. 0.2 out of 500 is a much smaller value. 0.003 over 0.9 is larger, right? It's larger than that. And 0.04 out of 8.46, 8.46 is 4 zeros and then a 223. This guy here is quite a bit larger. So when we see it here, this turns into this value. And then this value here turns into this, right? When we add them all up. Oops. Oops. This should be 0.00, sorry. This should have the same number of zeros there. I think the zero I'm missing is here. This is 4. One of these guys has a 0, sorry. Took my notes, I screwed up my notes. So I think it's 4 zeros there. And yeah, this is probably 4 zeros here. So once you square this value, it comes up with 4 zeros. So this guy here is larger than the rest. This is the closest the second guy is here. And so because it's the largest term in this sum, when we square them, the differences are exaggerated. And when we square root them, the difference remains. It's a funny thing, right? And then this is times 100%. This is equal to 0.0188 times 100%, which is equal to 1.88%. Oops, sorry. There we go. And so 1.88% is the uncertainty in this answer here. So let's see, we've got 0.25, oops, sorry. I'll get this on screen. 0.250 times, this is no longer equal, we're just going to use this result, 0.250 times 0.0188 equals 0.00 7. I'm sort of dropping sig figs here. We're just down to 3 and 3 and now 2, right? Because I know I'm not going to use more than 2 sig figs in the answer. And that is just a sort of an uncertainty practice. So this is 0.250. Actually, we can keep this last digit here, right? 8 plus or minus 0.0047. And this answer now is in molar. And now, to be perfectly honest, since this is an uncertainty, we can round this to 1 sig fig. Oops. And round it to 0.251 plus or minus 0.005 molar. This is our final answer here. So this is somewhat laborious, but once you've been through it a few times, it's not too bad. And I guess on the midterm, I'll have to have a very short example of this type of thing. Mm-hmm. So I couldn't have anything nearly this long or this extensive on the midterm. It'll probably just be like maybe 2 terms, possibly 3, but probably closer to probably 2 terms that you have to add up in this fashion in order to get an answer for the midterm. Something on that scale, right? Like, and maybe you'll just have to compare answers. Like maybe there'll be one, like this is a 0.5% error, and this is like this is like 0.03% or something like that. So we'll have to compare these two, one much smaller and what's larger uncertainty. And if you can predict which one will predominate in the answer, then that should work out. So how's everybody doing so far? Okay. I know I'm going kind of slow. I am. I don't know what's wrong with me today. I didn't have my coffee. That's what's wrong. Goodness. So, let's go back to the lecture notes here. We could say, so now we can, there's a couple of more iterations of this ammonia dilution, right? Actually, I solved this one too. I'll go ahead and put the solutions. I'll post the solutions to this guy that I got. It's this exact same process, right? You're just taking the same data, going through them and generating the same type of answer there. So, so let's go ahead and move on. Then we can talk about dilution for a moment. Right? And so what as an example here, what Dr. Harris has done in his book is he's going to compare a volumetric dilution with a gravimetric dilution. And and they're both going to be about tenfold, right? And and in the first case, we use a micropipette, right? And then we deliver 1,000 microliters into a 10 mil ball flask and dilute to volume. And then in the second case, we use a balance, and it's the same reagent here. We're diluting it by weight, right? So we're going to take 983.2 milligrams, which is about 1 mil, and add 9.026.6 grams of water, about 9 mils, right? So this, since the masses have to be additive, right? This is it's sort of an embedded weird thing, right? I don't like it. It's a little bit too tricky. But for volumetric stuff, when you always take an amount and dilute it to volume, right? But for mass, you have to add the amount that will make the total mass add up to say 10 milliliters in this case, right? It could also be 10 grams, right? As long as everything's the same temperature, and we would get the same answer if we added to 10 grams, right? So there's a 1 to 9 ratio of the amount that you add first and the amount that you add subsequently. Now, another thing I would do here is I would simply not tear the balance, right? I would weigh out the first amount, and I would add water until we got to 10, right? Or, it could actually be 9.83 grams, something like that. But in this case, it added 9 milliliters. So I don't want to get too much on this tangent of the difference between volumetric and gravimetric dilutions. But the idea is that the gravimetric ones, the weights always add up, right? If you add a small amount and a large amount, the two weights always add up to the weight of the sum, right? It's sort of a stupid thing to say, like put in 1 bean and add 9 beans, you got the weight of 10 beans, right? But it's not true for volumes, because more often than not, when you add a concentrated and a dilute solution, there's a tiny bit of change in volume. So in any case, that's all really neither here nor there in this question, right? The point is to calculate the uncertainty in these two cases, right? And so let's go ahead and do it Harris's way, then we can do it sort of my way, right? Well, this is actually works pretty well, right? So what Harris does here is he takes the ratio of the volumes, right, to compute a dilution factor, V final over V initial, right? And this is C1 V1 equals C2 V2, right? And so that's where this comes from. So the V final is 10 plus minus 0.2, and the V initial is 1 plus minus 0.3%, right? So what he's doing here is he's adding the 0.2 and the 0.3% as a root sum square. You square them, add them together, take the square root, and that gives you 0.036%. Right? And the 0.036% gives you you can divide this value here, which is the original concentration, by this factor, and then you can simply carry this factor into the 0.046, right? So, so you do the division, you divide this number by 10, you get 0.004, right? You keep this guy up here, you get 0.00 plus, and then what you can do is you convert this to molar, right? Basically there's actually two steps in this last transformation. You divide this value by 100, you multiply it through, and then you take that value and add it as a plus or minus here. It's kind of like changing the unit from percent of molarity to molarity. So, does that make sense to everybody? Is that clear how he did this last step here? Don't be shy. If you're feeling a little lost or I'm going too fast or anything, don't be shy to speak up. Or if I'm going too slow, then that's okay too. You can go ahead and speak up. And I'm not getting the comments right now. The chats. Oh, I think I pulled a paper. Okay, cool. So I'll go ahead and move forward here then. In the second case, he did the same thing, right? We take the two masses and we add them up, the uncertainties in those guys, in percentage, right? So 0.003 grams, this is the uncertainty on the balance, right? And 0.003 divided by 10, 0.003 divided by 9.98. Well, actually, he first aggregated them, right? Sorry, this is my bad. First, he aggregated them here. 0.003 squared is 0.003 squared is 0.042, right? And then the 0.042 squared, I'm not sure why he uses 0.03 here. What? In the dilution factor. I see. Well, in 0.042% of 10 is 0.04, and 0.042% of 0.98 is 0.03. So there's a couple of steps that are skipped here. That makes sense. So I'm not really a huge fan of the way he's doing it here, but that's okay. So this is the percent uncertainty in this, that's the percent uncertainty in that. And then you aggregate these two guys together by doing this transformation. You take that, square it, you take that, square it, you add them up, take the square root, and that gives you 0.0308. And then you add that to the answer here. So there's a little bit of a sleight of hand here because this answer here comes from down here. So, and what I can do is, I'll redo this in a different way for you, in a way that I think is a little bit more transparent, and hopefully it'll help you. So 0.046 divided by 10 plus or minus this value, right? This is going to be the new molarity. This is the original molarity divided by the dilution factor that's uncertain, right? Now the percent just comes right through. You multiply the percent out to get the answer. So this is basically saying that the gravimetric analysis is about 10 times more precise than the volumetric one. And that actually tends to make a difference in this area, but let's do another one in a slightly different way so that I can help you guys out, help myself out hopefully, to see how this is done. Okay. So in this case, what we're doing is we're okay, so this is a slightly different problem. We have we're trying to describe a volumetric dilution that would be more precise than using 1,000 ml micropipette, right? And a 10 ml vol flask. And I already kind of know the answer here, right? Because the smaller the volumes, the less precise in general, right? So I know that we're going to be going up to a 1 ml or a 10 ml pipette, and then from a 10 ml to 100 ml or 100 ml to a liter, 1,000 ml or 1 liter vol flask. So, so let's see how I did this, and then we can possibly move forward here. So, I see. I'm not exactly too wild about how I did this in my example either. Okay, so let's start from a basic place. Let's say C1 V1 equals C2 V2. This is the dilution formula, right? And let's calculate the uncertainty in C2. So C2 will equal C1 times V1 over V2. Right? This is our dilution factor, right? So C1 times V1 divided by V2 is our new dilution factor. Right? So we're going to let C1 and C2 be just variables for now, and let's calculate the uncertainty in this ratio V1 over V2. Okay? So if we use case 1 here, which is 1,000 microliters over 10,000 microliters, so this is a 1 over 10. This is the same as saying a 1 milliliter over a 10 milliliter, right? The precision on those values aren't the same, but that's essentially what we're comparing, right? What we want to know is the percent error in this ratio, right? So we could say R1, right, is equal to 1 milliliter over 10 milliliters. And the percent error in R1 is equal to the percent error in V1 squared plus the percent error in V2 squared, the square root of the whole thing. Right? So in the 1,000 microliters, we have a plus or minus value of 0.6%. That's just from a table. In the book. And then in the 10 milliliter, it has a plus or minus percentage error of 0.2%. That's also from the book. So if we add these up, then we've got the percent error in R1 over R2, right, will equal 0.6% squared plus 0.2% squared square root of that whole thing, which will equal about 0.63%. Right? That's how we would go about solving this guy. Now, number 2 here, let's try a 10 milliliter diluted to a 100 milliliter case, right? And the percent error in this, we'll take the 2% errors from these guys here, right? And those percent errors are going to be 0.4% and 0.08%. Right? So these are the two, these are, what we're doing here is this is a small pipette in a 10 mil. This is a larger pipette in a 100 mil. And the last one we'll do is a ginormous 100 mil pipette in a 1,000 mil flask, right? This guy here comes out to about 0.4%. And then in the last case, we've got 100 ml over 1,000 ml. And this is a pipette. This is a vol flask. Oops. And then this guy will come out to be, actually this is, should be an arrow here. This is going to be 0.2% plus, squared, plus 0.03% squared, which will equal about 0.2. This is once that's rooted, 0.20, right? So this is just showing that the 3 methods have different percentage errors. Error in method 1 is equal to 0.6%, which is greater than the error in method 2, which is equal to 0.4%, which is greater than the error in method 3, which is equal to 0.2%. little bit. So that's the whole point of that entire laborious exercise there, was just to show the difference in those errors. So so hopefully can I get a little bit of feedback from somebody or about whether this makes sense or not? Because I think it's kind of like a knife edge. Either it makes perfect sense or it's like you just don't, it just seems like a bunch of gobbledygook.
Good morning, Professor. I would say for me, the math isn't very complicated, but I suppose the concept behind it is what makes it a little more difficult to fully understand.
Excellent, excellent. Anybody else feel that way, that the concept is weird? Maybe even though the math is fairly straightforward? Okay, I'll take the deafening silence to mean, yeah, I feel the same way. So let's chat about that real briefly. We have about 5 more minutes in class, and so what I'd like to do is chat about how uncertainty is propagated, what the idea behind it, and why we use the Pythagorean theorem, right? You know, so when you have, let's say if you A plus B equals C, right? Then, you know, the uncertainty in A and the uncertainty in B are going to contribute to the uncertainty in C, right? That makes sense, right?
Yeah.
But yeah, but they don't actually add up, right? Because they fluctuate around 0, right? And they're independent, right? So let's put them on different axes to say that they're independent. Let's say that EA here fluctuates this much, right? And let's put this on the y-axis. E sub A. That's kind of tiny there. I think I better write this a little bit larger. That's right. So A plus B equals C. And then let's write E sub A. Let's write that as a value up here. And E sub B, let's write that as a value down there. Right? Now, if you just add them up, you can get E sub C, and it's not equal to E sub A plus E sub B. And these are not, you can't do that because E sub B might be negative when E sub B might be negative when E sub A is positive. Right? A lot of times their actual value will cancel, right? Because, like, you know, A might be 2 plus 3 equals 5, right? And if E sub A, if that's positive, E sub B is negative, positive 1 and negative 1, they'll cancel, when the error in C will be 0 in that instance, right? So, yes, in that instance, they'll be 0, but they will always be 0, right? So one way to address this is to keep them orthogonal, but add them as vectors, right? So this will be E sub C, right? So E sub C will equal the magnitude of E sub C will equal the root sum square of E sub A squared plus E sub B squared. You know, I don't think that was 200% clear, but does that help at all, Jorge? Maybe just a tiny bit?
Yeah, definitely. It's just to become a little bit clearer.
Okay. Do you have any feedback for me? Like, what did you mean by this? Or like, why are you saying that? Or like, I know that it's like sometimes if the explanation sucks, which that one did.
Oh, no, not at all.
Oh, come on. You should be clear. Oh goodness. Anyway, well, hopefully that helped a little bit, and we'll just pick it up next time. Hopefully, have a better day on Thursday, and we can have a little bit clearer session. But basically, next time we're gonna talk about exponents and logs, and hopefully we'll just get through this, and then some. I think we already did sig fig rules for these things. We'll just do one example. And the whole point of all this crap is basically just for this, right? Because we do pH and H plus, pH is the log of H plus, right? So there's that, and then there's its inverse here, right? And so let's get these two down, and then we'll go from there. All right, guys. Thank you so much for your attention today. It was a little bit fuzzy today. I'm sorry about that. But we'll do better Thursday. Okay? Alrighty, guys. We'll see you next time.
Thank you, Professor.
Thank you, guys. Thank you so much.
Thank you.
Excellent.
Thank
you.
Thank you.
Thank you. Oops. And Mitra, I want to hear from you more too. You're not asking very many questions.